The second part of the morning session here at the Weather and Climate Summit out here in Breckenridge. Our next speaker is Dan Leonard. Dan works for WSI Corporation up in Massachusetts, and his specialty is seasonal forecasting. So this has always been an interest of mine, and I think an interest of quite a few people here in the room, about how can that actually be done when you talk about making weather forecasts every day and having uncertainties out 3 days, 4 days, 5 days. How can you go out and do long-range forecasting? So Dan is here from WSI, and let's take a look at a little profile of Dan before we start his presentation. Okay, when we come out, you'll be here.
Dan Leonard, a senior meteorologist with Weather Services International, has become established as an industry leader in the field of energy forecasting. With dual degrees in economics and atmospheric science, he offers a unique perspective to traders, briefing clients on potential impacts to the oil, natural gas, and power markets. Dan has been featured as a correspondent on CNBC, Fox News, and the Weather Channel for expert analysis on everything from hurricanes to heat waves.
Dan Leonard is Weather Service International's chief meteorologist. We call him Wall Street's weatherman, and he just got off his morning conference call with energy traders. Dan, what'd they ask?
Aaron, you made a good point earlier. They really aren't too concerned about oil right now. Even though those of us on the East Coast have been watching it very closely, the traders, not so much.
Dan Leonard, WSI's senior meteorologist. Dan, when is this hurricane coming? Where's it going to hit? All that stuff. We need to know.
For 9 years, Dan has been a valuable member of the WSI team, a company which has pioneered the industry of detecting, forecasting, and depicting the weather. He is pleased to be part of an organization whose innovative spirit has led to a variety of advances in meteorology, including the world's most powerful forecast model.
I have a tendency to ramble on and on, so please feel free to just throw up questions at any time. We'll take care of that. Yeah, thanks. And also, I'm not really sure exactly how familiar people are with seasonal aspects of forecasting, like teleconnections, things like that. So if I'm going a little bit too fast, if I'm getting in too depth too early, just yell it out. I'll go back and sort of elaborate a little more. And on the other hand, if you want me to get a little bit more in depth, I can do that too. So again, at any time, feel free to just shout anything out. So I also put Dr. Todd Crawford here with me. He's actually the brains behind the operation. I guess I'm just the face of our company, but he's actually the one that develops a lot of the models that we use to do seasonal forecasting. So if you have any like really serious questions about our methodology, he's the guy to talk to. Or if you have any complaints for that matter, talk to him. So let me give you a little background on WSI. I know talking with a lot of you, you've all sort of known WSI for their media products. I mean, we have TrueView, Max, things like that. But a lot of you weren't familiar with other things that WSI does. And we're actually a pretty big company. We have 200 people, and we've been around for a long time. It's just recently, the past 10 years or so, that we started to get into our own type of forecasting. Usually we provided data all those years back in the 70s and 80s. Now we're in the process of switching over and becoming more of a forecasting agency. So some of the forecasting aspects that we do, we have an aviation forecasting department, forecast for things like turbulence for the airline industries. We also have an in-house forecasting department for media. So some of the smaller stations, when they don't have an actual on-air presence at their own local station, they use us for remote hits, and we can do that for them. The department I work in is the energy forecasting department, and we're primarily geared toward energy traders, guys who are trading things like natural gas, oil, and power. This is sort of what I do on a day-to-day basis. I talk to these guys who are trading, and the first row here, you see the natural gas, oil, and power. If you think about how weather plays a role in these different commodities, if you think back to Economics 101, the first thing you learn is about supply and demand curve, right? When you have an increase in demand, that's naturally going to push the price of whatever input you have up. And that's true with natural gas, oil, and power when it comes to weather. So, for example, during the summertime, when you have hot weather, that tends to people use more electricity when it comes to air conditioners, so that's going to drive the price of these inputs up. Same thing is true in the winter when you have cold weather in the winter, again, it drives the price of these inputs up. This next row, the wind, hydro, and solar, that's actually slightly different. This is a case where weather affects things on the supply side of things, not so much on the demand side. So for example, let's take hydro for example, up in the Pacific Northwest where there's a lot of hydro plants. If there's a lot of rain up there, you get an increased flow in your rivers, you get more generation in the hydro plants. So there's a case where you can actually increase the amount of energy that's into the system based on the weather. So this is an effect in the supply. You increase the supply of something like a hydro plant generating electricity, you're going to decrease the price. So there's a couple different ways that weather can affect economic things when it comes to commodities. Commodities down here, things like grains, corn. I mean, everybody's probably seen Trading Places, right? I mean, it's a classic case, the orange juice with the crop report coming out because of the big freeze down in Florida. So that's a case, you know, everybody pretty much knows about that. Insurance is a sort of a burgeoning industry when it comes to seasonal forecasting. I'm not going to get too much into that right now, but that really has to do with more hurricanes and tropical forecasting. Obviously, everybody, Gulf Coast and East Coast that works in the insurance industry really has a vested interest in having a good seasonal forecast when it comes to tropical, so they can sort of prepare and adjust everything accordingly. Maybe increase their insurance premiums for everybody on the coast when we come out with a exciting forecast. But here's an example of how weather impacts the markets directly. What you're looking at here is the price of natural gas futures over the past 3 months or so since October. And I like to use natural gas because it's probably the closest commodity that we have that's tied to weather and weather forecasting. Couple interesting things to note here. Back in October, so this is October 24th through the 30th, this is about the time where we and a lot of our competitors, the government, started coming out with winter forecasts. And generally, they were all pretty bullish. A lot of people were calling for cold weather, including us. And then we had that big snowstorm on the East Coast in late October. A lot of cold air came in behind it. And people, traders especially, were starting to get excited. We actually had a little bit of a spike up in the prices. And things were looking optimistic for the price of gas heading into the winter. But you can see since then, November right through December, it's just been a downward spiral. I mean, essentially, the price of natural gas, as a reflection of how warm it's been, hasn't been much demand for the natural gas. And you can see how steady downward trend it's been. So here's a classic case of where if back in October you had an effective seasonal forecast, let's say you were calling for warm weather for the major consuming regions, which would be the Midwest and East Coast primarily, you would have a lot of happy clients right now. Unfortunately, I don't think there were a lot of private companies that were calling for such an extremely warm winter back in October. I'll get into that more in a minute. We also do it on a short-term basis, though, too. That last graph was a 3-month period. This is actually a 1-day period of the same commodity, natural gas. This is actually what I deal with more on a day-to-day basis. It's not so much the seasonal forecasting as it is the short-term forecasting. What we primarily do at WSI is deal in the medium range, which is generally the 1 to 2 week period. And that's really important when it comes to the short-term traders. They really like to look at that range. If you get beyond 2 weeks, it's sort of things don't change too much, and they can't really trade based on that on a short-term level. And then anything inside 1 week, it's just we sort of already know what's going to happen, so there's not a lot of fluctuation there. It's really that golden window between 1 and 2 weeks that can really drive the markets. So let me take you through here on a daily basis what happened on this particular day. This is actually last Friday. This is Central Time, so roughly between 4 and 6 a.m. Central Time. This is about the time where we start updating our morning forecast for the medium range, and a lot of other vendors do the same thing right around this time. And you started seeing more wording in the forecast about potential pattern change coming up for the end of January on this particular morning. So you can see what happened with the price. The traders started coming in. They filtered in during the early morning, started getting some interest, and you see an upward rise in price through the morning. Then during the midday hours, and this is what I primarily work with, I do a lot of work with the 12Z models, blog for the traders, talk to the traders about the different models. When these started coming out between 10 and 12 a.m., you can see another big round of buying in the markets, and that really continued through the rest of the afternoon. So you have the 12Z GFS, the Ensemble, the European, all these models come in and they tend to drive the price up when there was follow-through. So we had colder morning forecasts, and that was followed through by colder midday model runs. So here's a case. I mean, it's a 3% rise here in 1 day, which is pretty good for a commodity. And you can see, and this is a classic case where if the traders sort of were ahead of the game, they were talking to us during the early morning hours, they sort of could have beat the curve, bought their gas early in the morning, and made a pretty good profit. So here's a case where on a short-term level, you can also have a really good impact on the markets based on the weather alone.
What's the sell-off before the morning models come out?
Right here. It's hard to say. I mean, there's a lot of intraday variability. My guess on something like that is maybe I see it a lot, they're anticipating sort of a bad run of the GFS, for example. So they'll do that a lot. If they sort of anticipate that it's going to be bearish on the run, meaning warm, they'll sell it off before it actually happens, sort of to try to beat the punch. But on this particular day, the GFS actually came in surprisingly cold. So everybody that sold off sort of got caught on the wrong way and then spiked back up the other way. But, you know, I can't really say that with certainty. I mean, there's a lot of variability that goes on in a short-term level that you can't always explain. So,
is there as much play in business in natural gas when prices are at these very low levels as opposed to when it's higher like it has been?
What do you mean by play?
Business.
Business is able to...
I mean, people buy and sell to make money at low price.
Yeah.
That's 3%, but it's not as much money.
Right, that's true. But we're still talking about 3%. If you look back in time, the variability of natural gas, we're at roughly $3 a BTU right now, which is insanely cheap. I mean, that's unbelievably cheap.
My wife and I are royalty owners.
Yeah. If you haven't switched over to natural gas yet, I mean, I don't know what you're waiting for. They're practically giving it away at this point. But back in the day, I mean, especially after Katrina and Rita back in the mid-2000s, we were up around $10 a BTU. So it's sold off so much. I mean, you still get those big intraday variability. The 3% change is pretty good. But back in those days, you used to get a move. I mean, today, what was it here? It was roughly a 10-cent move or so. You used to get 10-cent moves in a matter of minutes back in the day when a model run would come out. So the variability is much less than it used to be. You're right. But you still get pretty big percentage moves. So anyways, moving on to seasonal forecasting, which is actually what I'm here for today. Get through the dry stuff first before we can actually get into the meteorology. There's a couple of different model techniques that we use to do seasonal forecasting. So there is some science involved in this. It's not all just hand waving and hoping. There's a dynamical climate forecasting model that we use. It's an NCAR model. We run it at WSI. There's two different versions of the model that we run at the same time. Perturb it 8 different ways, each one. So essentially, we end up with 16 ensemble members. And we take the ensemble mean, which, as you know, is usually the most skillful, more skillful than just any one particular member. We also have 3 proprietary stat models. And this uses different indices and also some regression analysis and analog years as well. So here's an example of the way the stat models work. Here's all your different indices. We actually use 20 different ones. Here are your more typical common ones, and there's a bunch in there that you've probably never even heard of. And the different stat models weigh these indices differently. They also have slightly different algorithms. And then we essentially, in the end, come out with 3 different outputs from the stat models. And it's not important to look at each individual one. You're sort of looking for similarities and correlations between all 3 of the stat models. So here's the way it works. Once we're done, we take all the stat models, all the climate models, throw them all together, process them, blend all the outputs together, and then we sort of come out with a map that generally encompasses all the different models that we use. We put a human touch on it because that's not particularly good looking. We sort of skew it the way we sort of feel like things are going to happen, and then we come up with a final forecast that looks something like this. The way it works, we usually do about 2 forecasts per month for both the US and Europe. It's 1 main forecast and then 1 updated forecast as new data starts coming in. And it's for the next 3-month period. So our next update that I think we actually issued this week is going to be for the February, March, and April period. Skill scores, not great, but pretty good. We're in the upper 50s on most of the stat and climate models, which is pretty good. We're above that 50% threshold. And then the ensemble mean of all those is 61%. And then once we put that sort of human touch onto it, we can get it up to about 64%. So over the past 10 years or so, we're at that roughly 64% skill level, which is pretty decent. I mean, it's not good on a short-term basis, but for long-term, you're better than 50-50, you're doing pretty good. I mean, ask any gambler/trader out there if you can be better than 50%, and they're making money any day if you're at 50% long-term. So this brings me to another point, and I just have to sort of get this out of the way. What actually is normal? I told you we're 64%, and that's directionally correct 64% of the time. So, for example, you have a baseline. Let's say that's what we call normal. Well, the problem is nobody really is sure how to define normal. Normal is always changing. It's not the same thing as average. So the trick in this whole process is figuring out what the best definition of normal is. So when we score ourselves, for example, we're looking for anything above or below that 0 threshold. So if we say it's going to be above normal in Chicago and they end up 1 degree above normal, what exactly is that normal? And that's really important when it comes to grading ourselves. So basically here what you're looking at is there's really no sort of consensus on what the best definition of normal is. The general industry consensus right now is to use a 30-year normal. And I'll show you in a second on a graph that 30 years is not necessarily the best way to do things, but then again, it's hard to change the industry and sort of the industry standard at this point. Here's a graph of different normals if we use if we look at a timeline here. What you see on the y-axis is the mean absolute error. So if you look at this as the skill of using a normal as a predictor of what the next year is going to be. So if you take an average of the period, say average 10-year period, your mean absolute error as a predictor of what the next year or the next season would be roughly in this range here between 1.5 and 1.6 on the mean absolute error. So a lower error is going to indicate a better predictor of what it would be next season, and a higher error is a poor predictor. So not surprisingly here, if we're only using a couple years, let's say we only use the past 2 or 3 years of seasonal, let's say winter as an indicator, you average those together, it's obviously a terrible predictor of what the next year is going to look like. There's just not enough samples. And as you would expect, the more years you add in, the more it goes down. But what's interesting is you don't see a normal parabolic curve, meaning the more years you add in, it doesn't necessarily get better. In fact, if you look at the 70-year for the winter and the summer, it's actually pretty high on the error scores. In fact, much higher than, say, like a 10-year. So this is a case where you have to sort of factor in the fact that climate is really changing. And to use a 70-year period as your normal, as your base level, is not a good idea. So what we're really looking for here is areas where, in the graph, where you have the lowest mean absolute error. And there's a few areas that really stick out. This 15 to 20-year period here for both winter and summer, between 40 and 50 years, and then again at the 60-year mark. And there's some theories on why these particular ranges are better overall. It could be solar cycles, it could be the Pacific or the Atlantic cycle, but we've really been trying to push for more of a 40 to 50 year. You can see there's a really good correlation there, really low mean absolute error. So in honesty, the best way to do this, if we could really get the industry to change things and use that 40 to 50 year time horizon to set new normals. Unfortunately, it's probably not going to happen. The industry is sort of set in their ways. So just be aware that this 30-year period here is actually a relative high. So it's probably not the best averaging period to use. Yeah?
So you've only got 100 years in this observation. So at some point, you're getting the numbers to get too short, to get too far out. So I mean, how confident are you that if you're pushing for, say, a 40-something year, that in the next 40 years you'll get the same kind of plot you would get for this 100 years?
Well, yeah, you're right about that. But this is an averaging period not just of the past 40 years. This is looking back in time and regressing it so that what would have been the best forecast for the winter of 1980, and then you look at the past 40 years before that. So you're looking at it over the whole period. You're right that this doesn't necessarily mean that, just because this is history that, future results are better this way, but this is what we have to work with right now. And there is science to back it up. There's different cycles in both the Atlantic, Pacific, and the solar to sort of support that argument. And it seems that the 30-year normal period, we're sort of in between cycles, so it may not be the best way to do things.
Are you, for winters and summers, is this temperatures or precip, or how are you defining that?
Temperature. Yeah.
Raise your hand for a question so I can get you the mic. Come on, Matt.
Actually, Matt, that brings me to a good point. For the majority of the discussion, I'm really going to focus on temperatures. I'll do a little bit on precipitation. If you have questions about precip, just throw them out there. But For the majority of what we do at WSI, we're really focused on temperature for that reason that I showed earlier with the traders. It's really all about temperature and how things play. That's what really drives the markets. And you can sort of infer the precipitation from a lot of the charts I'm going to use anyways. I mean, you know that generally when it's cooler and you have troughing, you're going to get more precip, especially on the east side of the trough. So you can sort of infer that precipitation. There's actually not very good skill with predicting precipitation either. So that's another reason why I won't get into it too much. But back on this, here's an example of the 30-year normal. We just recently changed things. We used to use the 1970 to 2000 period as a normal. We just changed last year from 1980 to 2010. So this is the way things change. Obviously, 1980 to 2010 is going to be a lot warmer than the 1970 to 2000 period. So you can see that when we shifted the 30 years, we moved it up 10 years last year to reflect the new decade, things got a lot warmer. That baseline went up. So, for example, the upper Midwest, especially during the winter, it's a lot warmer in these 30 years than the previous 30 years. So we have to really account for that. Same is true in the summer as well. Summer is obviously a lot warmer now than they used to be. Here's just another way to look at it. U.S. winter temps, U.S. summer temps. The trend line in the green there shows a clear upward trend. Now, not getting into any sort of like anthropogenic debate here, the trend is really undeniable, and we sort of have to account for that every time we do a seasonal forecast, that things are changing, and we can't necessarily use this period back and through here as a good indicator, as a baseline for what is considered normal. Some pretty obvious things here. The summer trend, very warm recent summers. I think last summer was one of the hottest summers on record, but there's almost a slight acceleration upward here in the summer temps. The past few years have seen a downtrend in winter, and there's been a lot of speculation on, oh, is this actually a new normal? Are we starting to get into a colder regime overall? Obviously, this year's sort of put a kibosh on that, but I'll talk a little bit more about that in a second. But yes, I think this year we're probably going to pop right back up into here, and so we're going to get right back above that trend line, so the warming trend continues. A lot of times we get asked questions that is variability more now than it used to be? Basically, is the weather more extreme than it used to be? And here's kind of a cool graph. This is on the y-axis here. We have the rank of U.S. summer temperature rank and winter temperature rank. So if you start out in the bottom, this would be a relatively mild winter, mild summer, and then getting up to the top, you have very cold winters and very hot winters. So basically, this is just a measure of variability over the decades. And to answer in short, yes, variability is higher than it used to be, much higher than it was in the 1990s. Here's the extreme index. We were actually below normal on the variability in the 90s. 2000s, the past 10 years, we've been pretty extreme. Some very hot summers, some very cold winters. But so if anybody wants to sort of argue with you on the global warming causes more extreme weather debate, you can always just point them back to the 1930s when we had a 27.9 on the extreme index. Look at some of these summer temperatures back in the 1930s, just unbelievable heat during the summer. But we also had some really cold winters during the 1930s as well. So 1930s are really the benchmark for extreme weather. So if anybody tries to say that, oh, weather's much more extreme than it used to be, just point them back to the 1930s. Talk a little bit about summer. I'm going to keep most of my talk to the winter, just because it's a little bit more interesting, more relevant to right now. But you can see over the past 5 years, summer temps, just a straight upward trend. And you can see back in the 60s and 70s, we had a slight downward trend. But the trend recently has really been undeniable. So why is this happening? It's not simply global warming, otherwise we would just have a straight upward trend. So how do we really explain this on a sort of a bigger picture level? One of the tools that we use is called the AMO, the Atlantic Multi-Decadal Oscillation. And this is probably the best correlator to summer temperatures across the U.S. You guys have probably heard of this before. It's a dipole effect, actually a tripole effect out in the Atlantic. So it's usually bounded by warm temps, sea surface temperature anomalies in the north, warm sea surface temp anomalies in the south, and relatively cool temp anomalies off the east coast of the U.S. and the Canadian Maritimes. Now, this doesn't necessarily mean, usually in a tripole you would be warm, cool, warm. Doesn't necessarily mean that you have to have below normal temperatures in this region. It just has to be relatively cooler than the other two regions. And this would classify as a positive AMO or the warm phase of the AMO. Generally, the entire Atlantic is warm. Now, why is this important for summer temps? Well, take a look at the graph. This is the AMO index over the past, I don't know, 150 years or so. And you can see there's a couple of notable areas. One, back in the 1950s into the 1960s, we had a peak in the AMO. Then it dropped off pretty considerably in the 70s into the early 80s. And then recently, it's been on the upswing again. The past 5 years or so, probably some of the highest AMO indices that we've ever seen, at least in the past 150 years. So how does this correlate to summer temps in the US? Well, obviously the past few years, the past 5 years especially, very warm summer temps in the US. And if you look back into the 70s, we had some really cool summers, 70s into the mid-80s, and that corresponds with a relative low phase in the AMO. Same thing back in the early 1900s, some very cool summers during those years.
Hey, Dan,
Yeah.
Is there any physical explanation for that connection?
Yeah, I'll actually get onto that more in a second. Give me a few minutes, but I just wanted to sort of establish that there is a connection, and I'll explain the physics behind it in a second. So we can look at the same thing too with the winter. Here's the past 60 years or so of winter temps, and again, you sort of have that upward trend overall. And then here's the past 5 years or so where everybody started thinking, oh, we're going back into like little ice age territory. So obviously global warming can't explain necessarily this, especially compared to the summer temps. So let's take a look at a few things that govern winter temps overall, sort of a big picture. One of the primary drivers of winter temps over the US overall is the Pacific Decadal Oscillation. And that's essentially just a measure of Pacific temps. Just like the AMO is a measure of the Atlantic temps, PDO measures the Pacific temps. So as a general characteristic of a PDO, you tend to have a horseshoe shape area of sea surface temp anomalies. So during a positive phase of the PDO, you tend to have cold water in the central Atlantic, just south of the Aleutian Islands, bounded by an area of warm water or above normal temps. And the opposite is true during a negative phase of the PDO. You have warm temps in the central Pacific bounded by an area of relatively cool temps. And I'm sure you guys can easily pick up on the fact too that during a positive phase of the PDO, you tend to favor El Nino type signals. And then during a negative phase, it tends to support La Nina. But that's important. I'll come back to that in a second. So how exactly does the PDO drive the pattern overall across North America? Well, there's a response between the surface of the ocean and the atmosphere, works its way up. So if you imagine there's cold water in this region on top of warm water further south and east, if the air above those particular areas gets modified by the ocean that it's over, you would expect cooler than normal air over this region, warmer than normal air just to the south. So what would that do? Well, obviously it would sort of intensify a baroclinic boundary at the surface in this region. So you establish a tighter temperature gradient north to south, and that tends to enhance the flow, the westerly flow through this region. So eventually that works its way up, because if you enhance the westerly flow, you're going to develop lower pressure to the north, higher pressure to the south, with that clockwise flow and then the counterclockwise flow. That forces the gradient east, or I should say westerly gradient, and then you eventually work everything up through the atmosphere, and you'll develop a general vortex in this region, and then an anticyclone further downstream. So you can see how that manifests itself. It's what we call the Pacific North America pattern. The general thinking is that the PDO tends to drive the PNA type pattern. So this is, the PDO is essentially a measure of the sea surface temps, and the PNA is a reflection of the atmospheric pattern that we would see in any type of a PDO pattern. So here you can see the below normal height anomalies just over this region of colder water. Downstream you have above normal height anomalies, so essentially ridging across the western US. And then as the wavelength pattern continues, you tend to get troughing across the southeastern US. So during the phase of the PDO, it tends to drive the PNA pattern, and you can see here on the graph, just like I showed with the AMO, negative PDO patterns tend to favor cold weather, especially across the eastern US, and pretty much the whole country for that matter. And you can see some of these really cold PDO events line up really well with some of our really cold winters, especially in the late 70s. And then relatively warm weather through the 90s and into the early 2000s corresponded with positive phases of the PDO. And you can see over the past, I don't know, 5 years or so, there's been a a steady decline in the PDO, and that sort of goes hand in hand with why temperatures have been falling across the U.S. over the past 5 years or so. So there is a pretty good correlation there. Not quite as good as the AMO in the Atlantic, but there is a correlation nonetheless. Then, of course, everybody's favorite teleconnector is the NAO. Dr. Forbes talked a lot about this earlier, so I won't go too in depth because I don't want to essentially just go over the same ground that he just did. But as a general rule, you have lower pressure to the north over the higher latitudes, higher pressure south off the Iberian coast and the Azores, and that tends to promote a mild zonal pattern across both the U.S. and Europe. The opposite is true when you have a negative phase of the NAO. You have high pressure block up over Greenland, lower than normal pressures off the Iberian coast. That tends to buckle the jet stream, and you get general troughing and cold weather over North America and Europe at the same time. So it pretty much goes without saying that the NAO is probably the most important teleconnector that we have. One of the most unpredictable on a seasonal level, but probably, if not the most important, one of the most important teleconnectors to predict long-term temperatures. So here's a correlation, winter correlation temperatures to the NAO. This is obviously a positive phase of the NAO. So during winter, when the NAO is positive, warm temps across just about the entire country with the exception of California and the Great Basin. Interestingly, in the summer, the correlation isn't quite as strong. In fact, you have actually a negative correlation across the southern U.S. So this would be a positive phase of the NAO. You tend to get troughing across the southern tier of the country with cool temperatures, and ridging across southern Canada and the northern tier of the country. So interestingly, the summer correlation to the NAO is quite different than the winter correlation. And there is a transition period during the spring and fall that we always sort of struggle with. The difference is that in the NAO during the summer, the vortex is a little bit weaker and displaced north, so you tend to have ridging shift a little bit further north, and that would allow the subtropical ridge and or subtropical jet to amplify a little bit more. So that's the difference, and it's a little bit tricky to sort of, especially during the shoulder months between the spring and the fall, to guess when that transition is going to occur. Otherwise, the NAO is probably the best predictor that we have, especially of wintertime temps across the lower 48. Obviously, it goes without saying that there's a strong correlation between the NAO and U.S. temperatures. The most classic case is probably in the late 70s when we had some extremely cold winters. The NAO was also extremely negative during those years. And then last year, also we had some really cold temps, and that corresponded with a really sharp downward spike in the NAO. But you can also see during the 90s, we had largely positive NAO, and that really corresponded with some unusually warm winters. So I'll spend the next few minutes talking about ways that you can try to predict the NAO. It's not clear-cut. It's sort of a tough science, and we're not exactly sure how to do it. I mean, if we could have done it this year, obviously things would be a lot different. But I'll show you ways that we can at least try to predict the NAO on a seasonal level. So right here, let's go back to the AMO. That's the that tripole effect in the Atlantic. Here's a negative phase of the AMO. So I showed you the positive phase earlier. The negative phase would be cold water to the north, cold water across the tropics, and warm water off the east coast of the U.S. This is a pretty extreme case here where you have a really strong tripole effect. And then here's a positive phase of the AMO. We have warm, cool, warm. So if we look at what happens in a negative phase of the AMO, remember how I talked a little bit about the PDO in the Pacific, how that sort of works its way up from the surface of the water up through the atmosphere. Same thing happens with the AMO. So imagine here's your cool water. Your air up here just above the surface of the water is going to be naturally cooler than it normally would be. Same thing down in here, your air over the surface of the water in the central Atlantic warmer than it normally would be. You can imagine that there's some sort of a frontal boundary in here. You're going to enhance the baroclinic zone through that area, and naturally you would expect storm systems to develop along that baroclinicity area. So more storm systems through here, you're going to end up driving an upper level low back behind the storms, and as you can imagine, you would have lower than normal heights up over Greenland in the Davis Strait. Now the opposite is true during a positive AMO phase. Your gradient between this water to the north and this water to the south is actually weaker. So your anomalies, sea surface temperature anomalies and surface wind anomalies would be out of the east through this region. So you can imagine the anticyclone effect that this would create as you have a easterly fetch would tend to promote anticyclone up over this region. So that's a very basic understanding of how the AMO can drive the phase of the NAO. In this case, you would tend to have a strong polar vortex up over Alaska, so a positive NAO. And in this case, you would have a strong anticyclone over Greenland, so a negative phase of the NAO. Another thing we look at too is solar cycles. This is sort of a new field of study in how the solar cycles can affect high latitude blocking. And I sort of want to stress right off the bat that correlation doesn't necessarily imply causation. And I don't think that there's been really a strong paper ever written to prove that exactly how the dynamics work with regards to the solar cycle and the driving of the NAO. The general theory behind it is if you have an enhanced area of an enhanced solar cycle, so for example, you have an increase in sunspot activity, more solar radiation coming in, the area around the equator is going to catch that the most. You're going to, the ozone absorption in that region will drive higher than normal temperatures, actually push temperatures up in the high latitudes down in the tropical areas. So that will enhance your temperature gradient in high elevations from south to north. So essentially what you would get during that sort of an event is a stronger than normal polar vortex because you have a tighter than normal temperature gradient, say way up high in the atmosphere. Just one theory behind it. But there's really no denying that there is a pretty strong correlation. What I've done here is highlighted in red some of the extreme cases of solar minimums over the past 50 years or so. And you can see that some of the solar minimums, like in the late 70s, corresponded to really strong phases of the negative NAO. Same thing happened in 96. I mean, that was a pretty epic winter for the East Coast. And then recently, a real strong downward spike in the solar flux has caused some really negative NAO winters. And also the opposite is true. During phases when the solar maximum occurs, you can see sometimes in the 90s to around 2000, those were years that we had really positive NAO phases. So there is a pretty good correlation there. And we can actually take this even further back. If you look back in history, everybody knows about the Little Ice Age, they call it, in the 1600s and early 1700s. That actually corresponded to a time of very low solar activity. Virtually no sunspots ever detected during the late 1600s to about 1700. Very weak sun at that time. And you can see over in the graph here, this is probably our coolest temps in the past 500 years occurred during those times. You actually had a spike in the late 1700s in solar activity, and that corresponds to a spike in global temperatures. And then you had a secondary minimum, the Dalton minimum in the early 1800s, and you can see that this is about the time when global temperatures started on the downwards trend again. So there is a little bit of a correlation there between high latitude blocking and solar activity. So we do use that a little bit when it comes to putting that into the seasonal forecast, trying to guess whether there's high latitude blocking or not. Now, one of the things that a lot of amateurs and even pros alike like to talk about in the fall is the development of snow cover in the high latitudes across Asia and North America. And I guess the prevailing theory is that the more snow you build up in those regions during the fall, the better chance you have of sustaining the Arctic air and driving it south during the winter. Well, we did a lot of research on this idea, and we determined that there really isn't a good correlation pretty much anywhere. The one area that we found that correlates well is in Siberia during weeks 41 through 44, which is essentially October. That's really the only area where there's a strong correlation. See minus 0.5 on the correlation, which means if you have a good buildup of snowpack in that region during those weeks, you tend to have a pretty good correlation with a negative NAO during the winter months. If it happens before then or after then, really very weak correlation. You can see there's not much going on. In fact, there's actually a positive correlation once you get out to weeks 45 through 50. So the bottom line here is that it's only those particular weeks, and it's only across Siberia that really matters. So when we're making our October forecast, we really look to that region of Siberia during those weeks of October, hoping for a big buildup of snow cover if we want cold weather across the U.S. One other thing we look for when we talk about the NAO is what's called stratospheric warming events, sudden stratospheric warming events, I should say. A lot of you are probably familiar with this. The stratosphere itself is probably from about, I don't know, roughly here and up. So on your y-axis, this is height and pressure from the surface all the way up. And on your x-axis, you have time. So it starts out with January, goes to April. And what we're looking at here is the North Pole, so essentially what happens right over the Arctic Circle. And here's an example. Let's start out in early January. You can see up in the stratosphere, roughly about 10 millibars. Your stratosphere is relatively cool, below normal temperatures. So that's indicative of a strong polar vortex below normal heights in this region. But look what happens during mid-January, right about this point here. We completely flip it. I mean, this is an amazing flip. Within just about a week period, you go from below normal temperatures over the stratosphere in the Arctic to much above normal temperatures. That's what we call a sudden stratospheric warming event. It's a rapid change. And the theory behind it is, if you imagine a polar vortex, almost like, let's say, I don't know, like a tornado in a funnel, like one of those fun tornadoes that you make with the bottles. If you stick your hand into it, it completely disrupts the flow. You get a bunch of different little vortices that spin off, and then it completely kills the vortex. Well, the same thing can happen with the stratosphere vortex. If something disrupts that vortex, if you get some sort of a break into the vortex, it'll spin off into a bunch of different vortices, and then all of a sudden you get a rapid rise in temperature, and the vortex disintegrates. And the theory is that once this vortex disintegrates up in the stratosphere, it eventually works its way down through the tropopause and into the higher levels of the troposphere. So you can see that there's about a 10 to 14 day delay on when you get that sudden stratospheric warming event to when you see it manifest itself down in the high levels of the troposphere. So late January through just about all of March, we had a lot of high latitude blocking, aka negative NAO, during this particular year, and that was because the stratospheric warming event worked its way down and caused all that high latitude blocking over the Arctic and Greenland. Dr. Forbes mentioned earlier too about the AO versus the NAO. For the sake of argument, I'm going to spend most of the time on the NAO. There's a little bit better correlation with the NAO to temps over the US, but for those of you that don't know, the NAO is basically just a sort of a subset of the overall AO, Arctic oscillation pattern. But if I do happen to mention AO at some point, just sort of consider them synonymous. So in review, here's the primary drivers of the NAO. The AMO, solar activity, Siberian snow cover in October, and sudden stratospheric warming events. Those are the four things that we're looking at in October to try to predict the future in the winter. Yes?
I'll speak loudly. Is the Siberian snow cover, is there something causal there, or do you think that's a result of something else that's giving you a positive correlation?
It's a good question. I think it's causal. I think what it does is well, there's probably a feedback going on there as well. I think what happens is you tend to get, in that particular part of the world, you get a stronger than normal jet stream, polar jet, into Siberia. So you build up the snow cover, and there's a positive feedback there. It tends to keep the jet in that particular area. Now, why it's only those particular weeks, we're not exactly sure. We think that as time goes on, if you start to build up snow cover in December, big time in that particular area, that's actually going to amplify the polar vortex because you're getting colder than normal temperatures once the sun starts getting lower on the horizon. So it's really sort of that 3-week period in October that's the most critical. We're not exactly sure why. Not a lot of study done on that yet, but there is a pretty good correlation there. So. Okay, so moving on, back to the Pacific here, switch gears a little bit. Again, Dr. Forbes talked earlier about ENSO. Here's an example of El Nino. What happens during the positive phase of ENSO or El Nino is you have warm waters across the equatorial Pacific. That tends to drive convection. The MJO, Dr. Forbes mentioned it earlier, that's what you would expect to develop in this particular region. The downstream effect of the gravity wave that it would send out would tend to promote ridging along the west coast of the US and troughing in the east. So that's why during a lot of El Nino years you tend to get warmer than normal temps up in this particular region and then cold temps across the southeastern US. Here's the opposite that comes into play. Here's La Nina. Remember, during La Nina, you have a tendency to have cold waters here and warmer waters out in this particular region. So your MJO wave, or your area of enhanced tropical convection, is going to be here. That shifts everything back a little bit. So the ridge that you used to have in the western U.S. shifts back into the north-central Pacific, and then you tend to get a downstream effect of troughing in the west and then ridging across the southeastern U.S. So as a very simple sort of broad overview of ENSO, this is how it drives the pattern, especially in the winter. Not so much in the summer, but in the winter, this is really what ENSO does to the pattern over the lower 48. So let's look at the correlations here. Here's a typical La Nina type pattern during the winter. As you would expect, warm temps across the south and east, cold temps in the north and west. Strongest correlations are in the north central U.S. to cold weather, warm weather across the Gulf Coast area. Those are where the areas that we would typically expect to have the strongest correlation during both an El Nino or a La Nina year. If you're looking for an El Nino year, you would just reverse these colors. It would be completely opposite. So where does ENSO break down as a good predictor? Well, let's look at the past 3 years. Weak La Nina in 2008, 2009. Sort of what you would expect, warm temps across the south, cold temps in the north central U.S., but it didn't do so well in the western U.S. where you'd expect colder than normal temperatures. That didn't happen too much. And the mid-Atlantic and northeast was pretty cool as well. So the La Nina that year, 08, 09, it was a decent predictor, but not great. 09, 010, we look at most of the country is cold, especially in the central U.S. Well, strong El Nino, you would normally expect to have warm temps in the west and north central, and that's exactly opposite of what happened that year. So El Nino was pretty good that year predicting cold weather across the southeastern U.S., but across most of the rest of the country it failed pretty badly, especially in the north central U.S., completely reversed. And then 2010, 2011, you see cold weather across most of the Midwest and East, milder temps in the West, and again, that's pretty much the exact opposite of what you'd expect during a La Nina. The cold temps in the north central U.S., yes, but you would expect colder temps out in the western U.S. and then warmer temps in the southeast, and that just didn't happen. In fact, if you look at 2010 and 2011 compared to 09, 010, I mean, they're virtually identical. With the exception of an order of magnitude or so, they're pretty much the same, cold temps in the exact same region. Strong El Nino, strong La Nina. It doesn't make any sense. The bottom line is here, if you try to use either of those ENSO correlations for 9, 10, or 10, 11, would have been a really bad predictor. Okay, so going back to the PDO, I had this slide earlier. This is something I sort of want to focus on here. The PDO, when it's out of phase or whether it's in phase with ENSO. Now remember I showed you that during a positive phase of the PDO, cold water to the north, here's your El Nino. So this is a very strong positive PDO, El Nino type signal. The opposite is true with the negative PDO, La Nina type signal. Now what happens when they're slightly out of phase? Well, actually, sorry, let me go back. When they're in phase, El Nino with a positive PDO, you sort of get what you would expect. This is sort of your classic El Nino type winter, right? Warm temps in the west and north central, cool in the southeast. Well, what happens when they're out of phase? It's completely gone. The signal is just not even there. So this is a case where El Nino, you would expect warm temps across the west and north central U.S., but if you combine it with a negative PDO, the correlation just completely gets wiped out. You go from much above normal temps in the Dakotas and Montana to below normal temps, it completely gets obliterated. So let me just go back 1 second. This would be a case where if you have El Nino here, warm temps here, but the reverse were true up here. So you would have warm temps here, cold temps there. That's where it gets out of phase, and that's what you end up with as a solution. The bottom line here is there's very little correlation anywhere across the lower 48. Let me take a look at another example of how La Nina can be stratified by the NAO phase. Here's a pretty classic looking La Nina pattern, right? You have warm temps across the south and east, cold temps in the north and west. That's during a positive phase of the NAO. That's sort of what you would expect during a typical La Nina. Look what happens when you combine it with a negative phase of the NAO. It almost completely reverses. Just about your entire country is cold with the exception of maybe Texas and the lower Mississippi Valley. Everywhere is cold, especially in the north central U.S. So here's a case where if you tried to use simply La Nina correlations this particular winter, you probably would have failed because you would have expected it to be much warmer across the eastern U.S. than it was, and in the west as well. So just a quick review of ENSO here. Overall, if there's one thing you guys can take away from this whole presentation, it's that using ENSO itself as a predictor of seasonal temps is just not a good thing to do. It's pretty easy to do because it's a pretty easy to predict ENSO in itself, but as a predictor alone, it's not that great. And unfortunately, that's what a lot of people use, especially in the fall. The general public understands El Nino and La Nina. Unfortunately, as a predictor of future weather across the lower 48, for the next season, it's really not that good of a correlation. So I want to take you through and look at a couple of case studies that we have. Before we talk about the debacle that is this year, I sort of want to go back in time and look at maybe a victory that we had recently.
Can I pause you for a second? Wait a minute. You gotta get the mic. Can you go in, you talked about the NAO. Can you talk briefly about the Arctic oscillation and its either relationship to the NAO and how it was a factor in the last 2 winters also? Because it was negative.
Yeah, well, it's essentially the same thing. The NAO is just sort of a branch of the overall Arctic oscillation pattern. So when you have a phase of the NAO, it tends to correlate to the phase of the AO. As a general rule, the NAO tends to be a better predictor of temps across the North America than the overall AO. But your Arctic oscillation is just basically a measure of that polar vortex over all of the Arctic region. Okay, so if you have below normal heights in the Arctic, you tend to have above normal heights in the mid-latitudes, and vice versa. The NAO is more a measure in the North Atlantic, which really has a slightly more impactful effect on the lower 48 when it comes to temperatures overall. But to answer your question, I'm sort of using them synonymously here. When it comes to weather over the lower 48, you very rarely get an AO that's out of phase with an NAO. They almost go completely hand in hand. It's very rare to get a positive NAO and a negative AO. It just really doesn't happen.
Follow up on that. Do you use like about a 15-day rule when it goes negative, then you expect colder?
No, it can be instantaneous. It's a measure of the blocking. Yeah, I mean, there can be sort of a lag time, and I've seen people try to use the tendency or the derivative of the change in the NAO to predict where things are going to go over the lower 48 as sort of a lag time. But there's not a lot of evidence there to support that there's any sort of a delay. So if you get an instant block, you can get an instant trough develop across the eastern U.S. It doesn't take much time at all. Okay, so going back in time, 2007, 2008, this was a La Nina year, negative PDO year, and WSI's forecast at the time, we had warm temps in the south and east, cold temps in the north and west, and just as a point of reference, the NOAA's forecast generally looked the same, but they weren't quite as cold across the north central U.S. and western U.S. as us. And here was verification. So you did end up with a lot of cold temps across the western and north central U.S., warm temps in the south and east. So we did pretty well that year, and you can see we did add value compared to what you can get from the National Weather Service. Just looking at some of the stats here, you can see just about every single region we were directionally correct. I think the only area we weren't was the northern plains. It ended up being a little bit warmer than what we expected. But this was a pretty good year. This was a year where we considered this a victory. And a lot of the clients that we had were pretty happy because in some of the really important areas like the upper Midwest, this is a really important area when it comes to energy because it's normally particularly cold in that area, and they also use a lot of oil and gas to heat their homes up in that region. National Weather Service was calling for above normal temps in that region, and we called for below normal temps in Minneapolis and Chicago area, and we ended up being right. So this was a case where we were sort of happy with how things worked out. We successfully predicted that negative PDO would play more of a role this particular year and really drive that PNA pattern. Remember, the negative PNA pattern tends to correlate to cold temps in the west and north central U.S. with the trough here and then a southeast ridge. So this was a pretty simple year overall. It really didn't have a lot going on, but we did okay. Yeah?
Can you explain that anomaly in the northern plains as downsloping, or was it?
I can't.
It seems kind of icy.
Yeah. My guess is that year, maybe there was an anomalous area of snow cover, less snow cover than usual. It doesn't take a lot because you get a little bit of downslope coming off the Rockies in that particular region. You just wipe out the snow really quickly. So maybe that was sort of something that happened. But the overall 500 millibar pattern was a trough in this region. So we don't worry about it too much. I mean, you're going to get those sort of weird areas that sort of stand out. And besides, the northern plains, there's nobody up there anyway. So I don't think anybody really cared when we missed. So yeah.
Dan, just quickly, since Jones is failing miserably to get the microphone around, could you repeat the question when it happens?
Oh yes. Okay. Sure.
Just catch it. I'll just.
Okay. So that was the good part. Now on to this year, the not so good part. Here's the forecast that we issued back in October. And for basically the December through February period, we expected cold temperatures across the northern tier of the country, warm temperatures in the south, especially the south central U.S., and a little bit of cooling on the west coast. Just a breakdown at that time, December and January, we had really cold temps across the Midwest and northern plains at that time. We thought it was going to be a pretty good winter up there, at least the first part of winter anyways. And here's the verification. So this is for December. You can see we probably could not have had a worse forecast than we had in December. I mean, this really sort of humbled us. It was completely opposite. The one cold area down in West Texas and New Mexico, that was the only area, well, that was an area where we actually had above normal temps. So the bottom line was, in the most critical areas in the Midwest over and through the Northeast where we had below normal temps up in this region, it ended up being much above. I mean, breaking records left and right up in that area, and we just completely missed it. So let me go back in time here to October and show you some of what we were thinking and why we maybe went so miserably wrong. Down here we had an emerging La Nina event. Remember, during the summer it sort of waned a little bit, then it came on strong again. So we say, okay, we have emerging La Nina, strong PDO. In fact, I think in November we had a record PDO value. I want to say it was like -2.5 or something. It was crazy. But you can see why. I mean, just a massive area of warm temps out in the Central Pacific, bounded by this region of cold water. So very classic looking PDO signal here. So that led us to believe that there's probably going to be some sort of a PNA type pattern develop over the U.S., which would, again, favor a ridge in this region, a trough in the west, and then a southeastern ridge. So that was thinking number one. We had accelerating snow cover across this region on Siberia and northern China. So that was the area that corresponds during those weeks in October to a negative NAO during the winter. So if we got that big snow cover buildup in that region, we tend to promote a negative NAO. Same thing with the AMO. You can see it's in a positive phase here, mostly warm temps through the Atlantic. So those two things, the accelerating snow cover, the AMO, and also a relatively low phase in the solar cycle should have promoted a negative NAO. I never really talked much about this, but we had low sea ice up in that region, but that's pretty much basic there. If you have lower than normal sea ice, your ocean temps are going to be warmer than normal up in that area, which would tend to work its way up through the atmosphere and promote upper level ridging in that region. So this is what we were thinking at the time. These were all the factors we're sort of weighing and saying, okay, this could actually be a pretty cold winter, especially across the west and north central U.S. Yes, the southeast is going to be warm because it normally is during a La Nina negative PDO event, but we could still get some pretty good Arctic outbreaks across the eastern half of the country if we can develop that negative NAO, which the signal was there for. So at the time, there was a couple caveats that we looked at. First, Dr. Ford's talked about the MJO earlier. The MJO is just simply an area of enhanced convection in the tropics. It tends to propagate around the globe. And during the La Nina times, you tend to get your area of enhanced convection across the Indonesian area, sometimes as far west as the eastern part of the Indian Ocean, sometimes into the West Pacific. But during La Nina, it's never going to cross over into the dateline because the water is too cool there. The MJO wave just does not like to go into that cool area of water. So here was last winter. You can see that this blue and purple is the area of enhanced convection, and it's mostly between 80 degrees and 140 degrees, which is basically from here through about here. So all your enhanced convection last year was right in that particular area, which is really pretty classic negative PDO La Nina type signal. This year we were a little bit worried because look at where the next burst of enhanced convection was when we were making the forecast during late October and into the first part of November. It started out west of that 80-degree line, so it was actually back over in the Indian Ocean. And we were worried because the sea surface temp anomalies in this region were really warm, and they were actually cool over Indonesia. So one of our concerns was that if the focus of the MJO convection was more back here than here, that you wouldn't get that typical PNA type signal across the lower 48. Well, it turns out that our concerns were largely unfounded. Here's a slightly different view. Here's your area of enhanced convection burst in late October in the Indian Ocean. There was another one later, November, a little bit further east. Then you can see as we got into December, it propagated eastward right through the Indonesian area into the Western Pacific. This is a slightly different way to look at things. This is a phase diagram. You guys have probably used this before, but for those of you who've never seen it, you're looking down on the globe, and you can just imagine that here's the MJO wave over time propagating eastward. It does a little bit of a loop here, then comes back into the Western Pacific. So starts out in the Indian Ocean in October, then moves through the maritime continent in November and December, and finally emerges out in the Western Pacific. Also, for those of you who've never seen this, intensity of the wave is dictated by how far it is from the center. So the reason for this loop here is that the wave actually weakened a little bit through this time here, and then it re-emerged back in the same spot and got a little bit stronger again. So that's the way the MJO wave works, and that's sort of what drives the Pacific pattern. So we were worried about, the fact that convection might hold back through this region, but eventually through December it shifted to where it was supposed to be. So that isn't really a good explanation as to why things failed. Yeah, the bottom line is La Nina sort of acted the way she was supposed to, and the PDO was exactly the way it was supposed to. Here's where all your convection was. Indonesia and the West Pacific. Your mean ridge axis was right here through Hawaii and Alaska. It's a little bit further east than you would normally expect. It got onto the west coast a little bit, but that's generally what you would expect, is a ridge in this region, and then you should have had troughing over the lower 48.
Which led to some of that convection there, the severe flooding. I don't have it. I was going to say, is that what led to the serious convection that gave the big floods to Indonesia and everything?
Yeah. Yep. Completely MJO driven, yeah. Okay, so we can't blame the Pacific. We have to shift over into the Atlantic and the Arctic region. And it's pretty obvious this is 500 millibar height anomalies over the month of December. You can see lower than normal heights in the north, above normal heights across most of the mid-latitudes, except for in the southwest. There's a little bit of a split flow pattern here. And incidentally, that's really the only area that's actually had winter this year is in the southwest and West Texas, where that persistent split flow pattern has driven the subtropical jet stronger in that region and allowed for some snowstorms. Otherwise, you can see broad zonal flow. Here's where your enhanced jet stream would be. So your polar jet is north of the border, warm temps across most of the lower 48 as a result. So obviously, we can blame the NAO for this, as most of you already know. The NAO is extremely positive right now. It has been all of December. In fact, it's a record for most positive December NAO of all time. And the NAO really hasn't been negative for a long time. In fact, even back and through most of the fall, it was positive or slightly neutral. So obviously, NAO is to blame for this whole debacle. So let's go back and look at.
And then real quickly, though,
yeah.
You were saying that some of the predictors, as you said, La Nina, El Nino, it's very predictable, and the challenge is it looks like the NAO has so much influence over the eastern winter, and it's probably the least predictable factor.
Yeah. If you take away anything from this whole presentation, I think that would be it, is that essentially the predictable factors like La Nina and the PDO take sort of a backseat to something like the NAO. So when it comes down to it, predicting high latitude blocking or the strength of the polar vortex is really what seasonal forecasting is all about, and probably the hardest challenge that we have.
Is it more changeable as well in a shorter time frame?
Yeah, but it is an oscillation, so it can tend to go through, and also has a positive feedback. So once you establish a phase of the AO or the NAO, it tends to have a positive feedback because you have a strong polar vortex. You're going to increase the snow cover in that particular region in the high latitudes, and you get that positive feedback. So cold begets cold, basically, in the north, and then warm begets warm in the south. So yes, it does fluctuate. In some years, it goes dramatically from positive to positive, but that's not really what we're concerned about. We're really looking for the years where it overall average it out, and it's strong one way or the other. And this would have been a great year to say that, okay, we're definitely looking at a positive NAO this year. So I want to sort of go back and see if we can find any signals that sort of would have indicated to us that there would have been a positive NAO this year. First off, I talked about the stratosphere earlier with those sudden stratospheric warming events. Here's a curve of the stratospheric temperatures. I think this is, 30 millibars. So this is about midway through the stratosphere. And you can see that here's your average stratospheric temperature. And beginning in November, so we're making our forecast back in October. It's looking pretty good. But look what happened in November. We really started underperforming as far as temperatures in the stratosphere, which really was your first indicator that the polar vortex, at least over the stratosphere, was really strong.
How's that measured?
Temperature.
No, how is it actually measured? Santa Claus.
Question was, how was that measured?
I think using satellites, I want to say. I think. Is that true? Yeah, satellites.
And how do they parse out the stratosphere?
How do they parse out the stratosphere?
Sounders. It's a CO2 related relationship, so different emissions at different layers in the atmosphere.
Okay. Could you repeat that?
That was a really good
I
answer.
could say it more clearly too, probably. So satellite sounders are designed to measure a whole variety of wavelengths of emission from the atmosphere. They tend to be mostly CO2 wavelengths and the emission varies depending on the wavelength. If you have a wavelength that's very well emitted by CO2 molecules, then the signal that you get at the satellite is going to come from very high in the atmosphere. And if it's not well emitted, then it'll come from very low. So that's when you heard about atmospheric windows. Those are the wavelengths that are used to measure like sea surface temperature.
That was Jennifer Francis from Rutgers University. Go ahead, Dan.
Yeah. Actually, she's going to expound on a lot of what I talk about here on Friday, so that will be interesting. Looking forward to that. Anyways, if we look at the state of the stratosphere over the winter so far, obviously we're underperforming as far as temperature, so stronger than normal polar vortex. This was from January 8th. You can see here stratospheric temps. This is 10 millibars, so this is even a little bit higher. But you can get a rough idea that you have a strong polar vortex over the Atlantic portion of the Arctic. And obviously, once that works down into the troposphere, that correlates to a positive NAO.
Could you back up a second?
Yeah.
Point out a continent. Right, it's hard
Oh, yeah, sorry.
You can see
Should have traced it.
20 west.
Okay, so basically here's Greenland and Europe. So your strongest polar vortex in the stratosphere was essentially right in that bullseye negative NAO region, positive NAO.
blocking highs over Siberia and it's weaker than normal?
Well, this is in the stratosphere. It doesn't necessarily mean that it works down to the surface. There's a delay. Remember I talked about the 10 to 14 day delay? This is from January 8th. You don't necessarily have higher than normal heights in the troposphere in this region yet. I'll get into that in a second. But yes, right now in the stratosphere, at least as of January 8th, your polar vortex, which used to be up here, has shifted down into the North Atlantic just a little bit. So that could be important going forward. I'll talk about that a little bit more in a second. The solar cycle. Remember we talked that solar minimums generally promote negative NAOs. Solar maximums generally promote positive NAOs. And back in the fall when we were looking at things, we're still in a relative solar minimum. Remember last year, really low on the solar flux. And that corresponded with such an incredibly negative NAO event, especially last December and January. Well, look what happened just in the very first part of December and into early January. We had a big spike in the solar cycle. So that could be one of the reasons why we had such a positive NAO as well. Obviously, it wasn't quite as big of a spike as we had back in this region, but it was a big spike nonetheless, and definitely more than what we were expecting as far as solar flux. Finally, talk about the AMO. This is a comparison of last year at this time during October to this year during October. So some similarities. First, they're both positive. Obviously, this year is a little bit more positive. There's more warm water overall, but this year it was still positive. So when we're plugging all these variables into our stat models, positive AMO still, even though it's only 0.1, it should promote upper level blocking in the North Atlantic. Let me go back in time to October 2010. Everybody remembers the big high latitude blocking event we had during late November through early January of 2010, 2011. And interestingly, there was no stratospheric warming events during that time. All the blocking was basically from the ground up. It started out low and then worked its way up. Stratospheric warming events is the opposite. It starts high and works down. And it's really easy to see why in retrospect. You look at the surface temp anomalies in the North Atlantic just south of Greenland. Very warm, very cool water off the coast of Newfoundland. As you would expect, you're going to enhance the baroclinic zone through here, drive a westerly flow, works its way up. You're going to get a big time. I'm sorry. Let me back up here. Complete opposite. Yes, you're going to get an enhanced easterly flow, or easterly anomalies to the low-level flow. You're going to develop a big anticyclone up over this region. And then opposite is true down here. You'll have a low pressure down in here. So that's classic setup for a negative NAO. So this year was a little bit different. Still positive, but because most of your Atlantic basin was still above normal, slightly above normal. But the problem was, if you look in this sort of key area here, you're right near normal, just south of Greenland and Iceland, but you sort of have this pocket of warm water off the New England coast and off the Canadian Maritimes. And if you think about that, there's just not a very good correlation here, what you'd expect. In fact, if anything, this might actually act as a more of a negative AMO, because your gradient through here would be more like this. If you have a baroclinic zone, maybe like right through here, you're going to drive like this. So you would expect a vortex to develop over this region. At the time, we weren't really concerned about it because the overall AMO was positive, but this may have played a role, at least a little bit of a role. And going forward, I think probably what we're going to do is maybe ignore the AMO overall as a big picture and just focus more on this sort of boxed area of what's going on. So the AMO as a predictor overall, maybe not quite as good as we thought. It's more of a case of what's going on with these sea surface temps, say, between Greenland and the northeastern U.S. That's really key, we're thinking right now. Another problem that we had is snow cover. And this is a really important factor. I'm sure you're all well aware, but it's probably the most unpredictable factor of all. I mean, we can hardly predict snow, a week in advance, never mind a whole season in advance. So these are the anomalies compared to average. Look at generally 50 to 100% below average across the northern tier of the country. Your big bright spots in the upper Midwest, northern plains, and out in the Great Basin and Pacific Northwest. The only bright spot, I guess, in this whole thing is the front range of the Rockies down through the southern plains in New Mexico, where they've had, that snow based on that split flow pattern out there.
Is this October?
This is through December. Yeah.
That was basically one storm.
Yeah.
And it got
Yeah.
cold.
Yeah, exactly. But I guess that's all it takes down in that part of the country.
It was maybe one storm there in the high plains, but down into Mexico in the mountains, there have been a number of storms. We've had cold core lows dig down there and set for days and dump snow.
Yeah.
Yeah. But the bottom line is the areas that you want to see it, up in this corridor here, didn't happen. So I want to show you sort of an example of how things work. And a lot of times when we're doing forecasting, especially medium range forecasting, we tend to use the 850 millibar temps as opposed to the surface temps as a predictor. It sort of ignores the noise that you would see at the surface temperature anomalies, because once you get above the ground, you don't have those typical noisy things with sea level pressures that you would normally get in the longer range. So this is actually an analysis, but if I was looking at this as a forecast map, I would look at this and say, well, actually, we're right around average with the 850 temp anomalies across the upper Midwest. You can see, I don't know if you can see it actually, but we're mainly between -2 and 4 for the 850 temps up in this region, the Dakotas, Minnesota, and Wisconsin. But here's something critical to note. Look at the snow cover. No snow cover up in this region. Basically, you have to go into the Arrowhead of Minnesota, northern Wisconsin, then up into Canada to get any snow cover. Then look what happens when you look at the surface temp anomaly. So this is an analysis. This is actually what happened. Look at the surface temp anomalies, 15 to 25 degrees above normal in this area of the upper Midwest, Minneapolis up through Bismarck. If you're looking at this map, you're probably thinking, yeah, there's probably a cold front through here, maybe a storm here, warm front here. So this is post-frontal. A cold front has already moved through the upper Midwest and northern plains. Your 850 temps get back to roughly about normal, but look what happens with the surface temps. Still an absolute furnace. And that's a great correlation to an area where there's virtually no snow cover. Now look at the 850 temps up, say, north of Lake Superior. Again, roughly right around where they should be, 0 on the anomaly. But the surface temps in this region, much cooler, right where they should be, 0 to +5 on the anomaly. and that's because they have snow cover. So, so this is a classic case where we could have successfully predicted the upper level pattern. We could have predicted the 850 temps perfectly and said, maybe near to slightly above average, and we would have failed miserably at predicting the surface temps. And there's really just no good way to do it. Who could have predicted at this point in the season back in October that the northern plains and upper Midwest would have no snow? I mean, it's impossible. So going forward, is there any hope for us? Well, here I put up a couple of maps here. This is from a few days ago, but I just checked, and it's roughly the same. This is a 300-hour forecast, so this is getting into the end of January. This is the 10 millibar temperature anomalies. So this is way up in the stratosphere, and you can see what's going on here. Both the ECMWF and the GFS, both really increasing temps across the stratosphere during this time. The ECMWF in particular, right over the North Pole, a big, big warming event in the stratosphere. And then you can see in most of the mid-latitudes, you have that nice dichotomy between the strong ridging in this region and the troughing across the south. So the question at this point is, does this stratospheric warming event work its way down? Not all stratospheric warming events will do that. I'd say it's about maybe 50 to 60% of the time that you do have a stratospheric warming event that works its way down through the troposphere. But we have hope anyways. This is a much better looking view than what we had, say, a month ago, where there was a strong vortex over the North Atlantic region that I just showed you. And this is the latest GFS ensemble, 384 hours. So essentially what you're seeing here is the development of ridging across the North Atlantic. So maybe that is a reflection now of that stratospheric warming event starting to work its way down a little bit. You have positive height anomalies in this region. You really don't have much troughing in the east yet. But as you were saying, maybe there is a little bit of delay here. We can build up some ridging in this region. Maybe beyond 384 hours it gets even stronger because of that stratospheric warming event, and we can dig some deeper troughing into the east. The only problem still, though, one of our strongest signals is this big vortex over Alaska. So it's displaced. It's not where it was over the North Atlantic and the Arctic, which is better, but still, when you have a strong vortex in this region coupled with ridging in the southwest, you're going to get a tremendous flux coming into the west coast. So good news for you, Matt, I guess, if you want some snow up in the northwest and up into Vancouver. But for the rest of us, it just means a return for a mild zonal flood of Pacific air crossing the country. So there are some positive signs here, but there's still some caveats that we have to look out for. This is a better looking chart than what we've seen pretty much all winter, but it's not 100% guarantee yet. This is the latest ECMWF weekly. Just came out last night, so you guys are getting a first look at this. This is week 4, so this is heading into the first week of February. And you can see pretty good blocking developing up across northern Canada and the North Atlantic, and associated troughing down in the eastern half of the country. Big ridge out on the west coast, though. So that might be sort of a sneak preview of things to come. It's unfortunate that we can't really get rid of this vortex over Alaska, because that's really what's messing us up at this point. But anyways, this is a sort of a hopeful sign that we can get at least some more normal temperatures across at least the eastern half of the country. If the Euro Weekly is right in this case, there's really not much hope for California getting into a colder, snowier pattern than what we've had. So to sum it up, here's what our outlook is for the next couple of months, February and March. We still expect cold weather to develop across the northern tier of the country, especially during March, as that southeastern ridge gets suppressed. There's a low confidence forecast, obviously. We had to change things big time in our update for January for obvious reasons. But we do expect that high latitude blocking to develop sometime in February or March, and that should drive colder temps down into the lower 48, especially in the north central U.S. Lowest confidence forecast is probably on the west coast, especially California. Based on a lot of the data that I'm looking at right now, we'll probably get some sort of a subtropical ridge in this region. So if I were changing things, I would probably whittle these colder temps back just a little bit. But I am pretty hopeful to get at least some cold weather across the northern tier of the country. Honestly, all that it will take is one good snowstorm for the northern plains and Midwest, and then we can really reverse things, reverse the course of what we had. So that is it. Here's my contact info and also Dr. Crawford's info. So if you have any more questions about this stuff, shoot me an email.
Dan, thank you very much.
You said you deal with the energy traders.
Yeah.
Is there a group of folks that deal with like the agricultural?
Yes.
And so they're looking at the same data that you're looking at?
Essentially, yeah. They're mostly more on a short-term basis, especially you know, the wind and hydro type things. Those guys deal on mostly like a 0 to 7 day basis, because when it comes to precipitation, it's really unpredictable on a longer term. So
like the winter wheat, Northern Plains winter wheat. It's
exactly, shorter term basis. Right. You know, storms change track all the time. So, but yeah, I mean, right now the wheat crop is in trouble out there. I mean, they haven't had much precip. So.
Dan, great stuff. You're considering the bust of this winter's forecast. Do you plan on maybe going back and looking at, you know, where the caterpillars furrier, where the, you know, the nuts that were being gathered less? Nothing scientific like that?
No. Yeah. No acorn index, no.
Dan, you said you were going to concentrate more on temperature. Precipitation was harder, but any thoughts, any late thoughts about changes in the precipitation forecast, particularly for the Southern Plains where we had such a bad drought?
Yeah. Well, I mean, if it's any good news, it's that this area of Texas has had a lot of precip over the past couple of months.
And it helps, but our wintertime amounts are a lot less than in the warm season.
Right. Yeah, that's true. And unfortunately, I think the pattern going into February, March, and then beyond is going to flip. And I think we'll go back, unfortunately. I don't like to say that, but there's really not a lot of evidence to support this big split flow pattern that we've had to continue.
One more question about the precipitation. I know you didn't touch on that very much, but it seems to me that the dry area is starting to push farther north into the Corn Belt.
Mm-hmm.
And now with no snowpack up in South Dakota,
right,
which is what they need to set up that moisture,
mm-hmm,
we could be looking at maybe drought conditions up there coming up this summer.
Yeah, it's not a good situation. I mean, you got the wheat crop out in here, you have the bean and the corn crop through here. Not a good situation. I mean, we're way below average. We really need a pattern change to develop. And if something like this happens, this is way better, because you imagine your frontal boundary would be right through here, and you would have most of your low pressure tracks up through here. So snow up here, rain, thunderstorms down here. Maybe we could improve things. So fingers crossed this will actually work out in February and into March.
Dan, great stuff there. Several graphs ago, when you were doing your verification of last year's La Nina, you were using December through February as your verification period. And while that was accurate for that, if you extended that out through March and April, we ended up having a pretty typical La Nina year, at least in the West when it comes to mountain snowpack. And we use La Nina as one of our best seasonal forecasters for mountain snowpack. Mm-hmm. And it correlated really well with the graph you showed of the MJO, which really started peaking in late February and then into March. And I hadn't seen that before, but I noticed that correlation. So I'm just wondering if, basically if you could say that it was a late La Nina for us last year, because we didn't get much going on through January and most of February. Yeah. And this year so far sort of the same thing, and maybe it's going to switch again.
True. That's a good point. And there are indicators that it is going to switch. Dr. Forbes actually had a slightly different PNA/MJO graph where he showed how the polar jet gets displaced to the north and Pacific jet undercuts it and drives all the pineapple connection into the Pacific Northwest. There are some indications that will in fact happen during the second half of winter versus the first half, because I know you guys have been pretty dry up there, especially south of Portland.
Dan, Brad back here in the corner. Great stuff. I've been doing some seasonal forecasting for a while, and all this stuff is really cool. I was interested, though, do you ever look at lunar cycles or Hobmuller diagrams still?
No, I don't. I mean, I think we've gandered at it, but I think maybe we'll take a harder look at it. That and the Acorn Index, I think, yeah. Yeah.
Okay, I have a question about this. Most of what you've looked at, your techniques, flow in one direction, basically sea surface temperatures driving atmosphere. Do you look at what cycles in reverse? Because this is a nonlinear system, and certainly there must be some impacts that way.
Yeah, well, most oscillations in general have a feedback. So if something happens at the surface, it drives aloft, and then what goes on aloft drives what's going on at the surface. I mean, the NAO is a classic case of that, where if you have a strong polar vortex, it tends to create more snow, more Arctic sea ice in the North Atlantic, and then you get that positive feedback loop. So yeah, there is a correlation there, but the only way to sort of use it as a predictor is to start with what you know. What we know going into, say, the fall is sea surface temps. So we use that sort of as a predictor of things to come. But obviously in this situation, what goes on at the very bottom of this whole cycle isn't necessarily the best predictor. And the only way to predict upper levels going that far out is to use things like the solar cycle, the stratospheric warming events, which is what I talked about. Find things that might change things from up top and work them down to the surface. But it's a complicated game, and there's that feedback cycle there. And once you establish that cycle, it's very hard to break when you have a very strong oscillation pattern like we've had this year.
To Dan from Dan, something you showed earlier really fascinated me. The AMO, or I'm sorry, the PDO and the ENSO connection, when they're out of phase, you really have lousy predictability of, you know, with the ENSO, La Nina or El Nino.
Mm-hmm.
How often does that happen? Do you have any stats on that?
It's not very often, but it's more often than you would think. I think it was this one you're talking about, right?
Yes, right there. And the one before it. But they're in phase now, right?
They are in phase now, yeah. I forget what year it was. It was a couple years ago where they were completely out of phase, and we completely threw out ENSO as an indicator at that point. But that's I would say maybe, and this is, I don't have exact stats on this, but I would say maybe roughly 30% of the time you have an ENSO event, it's out of phase with the PDO. But the important thing here to remember is that when it is out of phase, you should probably just ignore it. That's the bottom line. But this year they were in phase, so we didn't ignore it. I mean, you had a very negative PDO and you had La Nina, so that was a pretty strong indicator going into the winter.
Okay, we have no other questions in here. We do have one thing that I wanted to remind everybody of, and that is at 1:30 this afternoon, Mountain Time, we will be opening up a live chat discussion with Dan, with also Dr. Greg Forbes from the Weather Channel, and also Bruce Thomas, who talked to us today about NOAA Weather Radio. So feel free to join us back at 1:30 after this particular session, and that'll give you a good opportunity for viewers around the country who are watching the Twitter feeds, who are watching this live stream. And I do want to say that we doubled our number of viewers from yesterday. We now went over 500 today, so that's terrific for our first live streaming Weather and Climate Summit here at Breckenridge. Sorry, just updated 600. So this is terrific. We are going to also be archiving these presentations. We're going to be making them available on our YouTube channel for the summit. It may not happen this week, but you can probably look for them next week if we get some time to upload them and make sure the file sizes are good. Then it may happen this week as well. So please come back and join us again at 1:30 to ask questions. I also wanted to acknowledge the audio-visual folks here in the Breckenridge area. The image audio-visuals folks have provided the lighting, the HD cameras that we're using, the rear projection screen, and the pipe and drape that you see up here to make this upgraded look to the Weather and Climate Summit. So please, if you have any audiovisual needs here in Breckenridge or elsewhere around the country, give them a call, look them up on the web. They've been very, very helpful to us here at the Weather and Climate Summit. The other thing that I'd just like to say is tomorrow we have a session which is going to be a pretty in-depth, exciting session for those of you who forecast, and that is Jim Ledoux from the National Weather Service Warning Decision Training Branch is going to talk about BuffKit and using BuffKit to do improved forecasting, to look at all sorts of atmospheric parameters. And then after the break, he's going to come back and actually do a forecasting workshop on BuffKit. And so the interesting thing is he'll have the opportunity for all of you here locally to download the software and to download the scenarios that he'll be talking about with the data and all that stuff. So we'll have that instruction for you. I'll have to talk to Jim to see if that goes for the online audience, but I think it's probably locally here to get that done. So it could, Jim says it could be anybody. So those of you who are forecasters that are watching online, you might have some excitement in that you could use BuffKit and go through a real-time workshop. So I think that's it for the announcements during the stream. We have some local instructions we'll do once we're off the air. Does anybody have anything else? Okay, so that's it. Thank you so much for joining us online today. Please come back again tomorrow, and Thursday and Friday we have very exciting sessions as well dealing with climate science and the changes that are happening there, so you won't want to miss that. So thank you very much. We'll see you once again back here at 1:30 Mountain Time this afternoon.